In this course, we shall derive and analyze numerical methods for the solution of various problems. We shall discuss the following topics. In the first topic, we shall discuss the numerical solution of nonlinear system of algebraic equations. We shall construct methods for finding the roots or zeros of a transcendental or a polynomial equation in one variable. Then we shall extend the methods for the solution of a system of nonlinear equations. In the next topic, we shall construct methods for the solution of linear algebraic equations and matrix eigenvalue problems. In the next topic, we consider a data or a table of values and construct the polynomial that fits this data exactly. This polynomial can be used for interpolating or predicting the value of the function representing the data at any intermediate point. This polynomial may also be used for various other operations like differentiation and integration. In approximation, we shall deal with approximation to a continuous function or to a function which represents the given data. In the next topic, we shall use the interpolating polynomial of a given data to find the derivative if it exists of a function at a nodal point or at any intermediate point. We shall also construct methods to numerically integrate a given function or to integrate a function that represents a given data. With the advent of high speed computers, it is now possible to numerically solve many complex mathematical models that represent the physical processes. A numerical method produces numbers as the required solution of the given problem. Many types of errors arise in solving a problem numerically, and these errors must be kept under control, otherwise errors dominate the solution finally. There are many books that are available on numerical methods. Few of the books are listed here. Analysis of numerical methods by Isaacson and Keller, Introduction to Numerical Analysis by Froberg, a first course in numerical analysis Ralston and Rabinowitz, Elementary numerical analysis, an algorithmic approach by Conte and Devor, Numerical methods for engineering application by Ferziger, Numerical methods, a software approach by R. L. Johnston, Numerical methods, software and analysis by J. R. Rice, Methods for numerical integration Davis and Rabinowitz, Numerical analysis, mathematics of software by David Kincaid and Cheney, Numerical methods for scientific and engineering computation Jain, Iyengar and Jain. We shall follow the course material given in this last book. Let us now define errors, discuss about the sources of errors and their effect on computation. Now, in earlier years, simple mathematical models were constructed to represent various physical processes using many approximations, so that the problem can be solved analytically. There were no avenues other than analytical methods in those days, but these are very approximate solutions. But with the advent of the modern computers, the models were now refined further and further, removed many approximations, and ultimately they have come across a model which could be without any approximations. Like for example, you can have weather forecasting model, or the very difficult problems are the nuclear reactor problems. The problems of very complex natures have been now constructed, but then these problems cannot be solved analytically. Therefore, a new branch of mathematics, the numerical methods, has come into existence to study or to solve these particular mathematical models. What does numerical method give? A numerical method is constructed to give a typical problem. That means it is particular with respect to this. For example, if we said solution of linear algebraic equations, we shall say that these are the methods that you can use for solving the system of linear algebraic equations. Similarly, therefore, a typical numerical method is constructed for a given typical problem. What does it finally give you? It gives you finally numbers as the answers. It says that these are numbers and take them as the solution of your problem. Therefore, it is necessary for us to see what kind of errors have gone into this. Are the numbers that we have got have make any meaning or not? Are they correct solutions, or are they embedded with some errors which is unknown to us? Therefore, it is necessary before we actually construct numerical methods, what are errors, what are the sources of errors, do they get magnified, and if they are magnified, do they spoil the numerical solution, and what is final outcome, how accurate or how reliable are the numbers that we are producing outputting from the computer. So, let us first of all define what is error and then what are the sources of errors. Now, as you all know that error is true value minus approximate value. So, that is just simple definition of an error. However, the error could be positive or negative, because the is a true value could be on either side of the approximate value, therefore, it could be positive or negative. Therefore, I would like to study what is the absolute error, so that we can talk of the magnitude of the error and say this is the error that has been made. Very often these absolute errors could be if the problem that we are solving has a solutions which are very small, or problems in which the solution is very large, then absolute error is going to be very small or very large. Therefore, suppose the order of magnitude of a solution is 10 to the power minus 5 and you get absolute error is 10 to the power minus 6, you may think that it is a very good solution, but it is not so, because we have to talk of the magnitude of the solution of the also into account. Therefore, a good indicator would be relative error, so that we have error divided by the true value, so that it will give you, it will take care of both the cases when the solution is very small or a solution is a very large quantity. So, usually relative error is a good indicator. Then we would like to look at what are the errors in computation that would arise in general. The first thing is your round off error. What is the round off error? You already know what is round off error, but let us formally define what it is. It is a quantity r, we will call it as r, which must be added to the finite representation of the number in order to make it the true representation of that number. That means, we are given a number which we want to carry out for computations either by calculator or by the computer. So, this number has to be given a finite representation, and whatever is left out will be the round off error for that particular problem. Now, let us take a very simple example. A simple example is we take 1 by 3. So, you may be keeping 4 significant digits. So, we may be writing 1 by 3 as 0.3333, and whatever is left out in the, it is an infinite representation, what is left out of this is your round off error. For example, all rational numbers, the roots of most of positive numbers, all of them would give us to round off error. Therefore, there is nothing we can do about round off error to stop it. Round off error is always there in any capital number, and round off errors when is not under the control of the user. What we mean is, when we go to the computer and we are putting these numbers on the computer, therefore, the round off errors is not is under control. It is, I will just discuss little bit more later, but this is round off errors is not under the control of the user. The other thing is the truncation error. Truncation error is a quantity t which must be added to the representation of a quantity in order to make this quantity exactly equal to that number. It arises due to use of approximate formulas, usually based on Taylor series. Now, if you want to write down for example, if you want to get the value of exponential of x for small x, I may approximate it as 1 plus x square by factorial 2. Now, whatever is left out in this approximation will be the truncation error, and this is mostly, for example, if you now look at the modern day computers, most of the functions are embedded in there. For all the major functions are all embedded in the computer, it automatically gives you, and those were evaluated by certain formulas, and those formulas also have got the truncation error. So, that part is called the truncation error. Now, let us just see how this error comes about. Now, if I write the Taylor series expansion of a function f x about a point x is equal to x naught, I can write it as f x f of x naught x minus f x naught f prime of x naught, and then theorem plus r as the remainder, where r is this remainder given by x minus x naught to the power of n plus 1 factorial f n plus 1 of xi lying between x naught and x x. There are various other forms of the remainder, but however, we shall use this particular remainder in our analysis to do later on. Now, what we were stating earlier is, if I now take this Taylor series and I now truncate it up to certain terms, then whatever I am leaving out will be the truncation error in that particular problem. Now, let me take the simple example, few examples. If I take sin x and I write approximated as x minus x cubed factorial 3 for small x. Then I would like to look at what would be the truncation error in this particular problem. The truncation error, if we just go back to this slide, if you look at it, if I now say that this is my remainder, from this I can find out what is the truncation error in my given problem. Therefore, if I write this as this, the truncation error would have the fourth derivative. Therefore, I need what is the fourth derivative. I can find, if I take f x is sin x, I can find the fourth derivative of this. 4 times derivation gives me sin x back. Therefore, truncation error is x to the power of 4 by factorial 4 into f4 of xi, that is sin of xi. Now, here you can see that we are expanding about the point 0. So, this is x minus 0 whole cubed by factorial 3, and hence here truncation error also will be x to the power of 4 by factorial 4 into sin of xi. Now, I can always bound this by taking its magnitude. So, if I write it magnitude, I can write this maximum of magnitude of x to the power of 4 divided by factorial 4. Magnitude of sin xi is always less than 1. So, I can simply write maximum of x to the power of 4 by factorial 4. Now, this maximum can be determined when once in the problem it is given that we are using this approximation for say x is from 0 to 0.001 or x from 0 to 0.05. So, when once you given the interval in which this formula is being used, I can find out its maximum, because maximum of magnitude x to the power of 4 can immediately be determined, and I can say that this is the largest truncation error that would be done while evaluating this in the given interval. Similarly, another example is if I take exponential of x as 1 plus x square by 2 again for small x, then I have retained only terms of the second order. The truncation error would contain the third order term. Therefore, I need the third derivative of exponential of x, and third derivative of exponential of x is e to the power of x, and therefore, the truncation error will become x cubed by factorial 3 into exponential of xi. Again we are expanding about the point 0, therefore, I will have here x minus 0 to the power of 3 this, and I can again bound the error as magnitude of this is maximum of magnitude of x whole cubed by 6 into exponential of xi. Again, if once we are given the interval in which we are evaluate using this for small x, again as I say, for example, from x is equal to 0 to 1 it is being used, then I can find that the maximum would be in the interval 0 to 1, maximum of magnitude of x is 1, exponential of xi will be 1, exponential of 1, therefore, this maximum will be 1 upon 6 into e to the power of 1. So, it is simply e by 6 will be the maximum bound of the error. So, I can find out the bound for the errors given any particular formula, and then write down its Taylor expansion and retain up to certain terms. We can always find out what will be the truncation error in our problem. Yes.
So, why are we taking it only for positive x? I mean, we can have small negative x also.
Yes, that's why we put here magnitude of x. We get here truncation error will be x minus x 0 to the power of 4, but here we have written magnitude. So, it would be positive or negative. Yes. Now, the next thing is truncation error is in the control of a user. That means truncation error is in our control. If we need better approximation, we can take more terms in the Taylor series. Suppose you say that you want an accuracy of 10 to the power of minus 6 in your solutions. We can find out the number of terms that we require in a Taylor series, and then use that many terms, say 10 terms or 11 terms, so that we get the accuracy of 62 places. Therefore, the truncation error is in the control of the user. So, there is no difficulty about that one. Now, then what will be the total error in a computation? The round off error plus truncation error and various other errors that we will now describe what are the other errors that can arise. Besides the mistakes that we commit, there will be some other errors. Now, one of the most important errors that will arise is the machine epsilon. Now, what is machine epsilon? That we know that all our computers have got finite word lengths. Either we may have a 32-bit word length or we may be having 64-bit word length. If we take a 32-bit word in the machine, then 1 bit for sign is used, 1 bit for sign of the exponent is used, 7 bits are used for exponent, and 23 bits for the value. That is your mantissa. I mean, that is how the computer takes in. Similarly, it will be almost be doubled. This part will be more than doubled if you go for a 64-bit word, and the the reason why we are saying is from this we would know when we put a number to a computer what is the accuracy that the computer is maintaining for this particular number. Now if I now look what is this 23, so I can go about by taking this 2 to the power minus 23 and find out what will be the approximate value for this one. So the accuracy is 2 to the power minus 23, approximately 7 decimal place accuracy. So if I go to the computer the 34 bit, that is what we have, then if we can expect 7 decimal place accuracy in each number. Now we usually call this as a single precision value. If we want to have more accuracy, then we can go for, in the you must have all be using, we can define the double precision variable, and then so that the double precision can be used, then it will be more than double the 4 decimal places, because you can see that if I just go back once to this again, we are using only 1 bit for sign, 1 bit for the sign of the exponent, and 7 bits for the exponent. Therefore if you go by a 64 bit length, this mantissa length is going to increase. Therefore instead of say 14 decimal places, it would be about 15-16 decimal places will be accuracy that will be obtained. If some problems the solution values are too small and you will have to get them accurately, we can go for multiple precision. We can also define the precision 4 times precision also, except that the time that is taken for computations are enormous, so that it will, the computer will allot 4 words for each particular number. So you can have a multiple precision also defined as this. Now therefore when a number is used, it is only accurate up to the accuracy of its machine. We are talking its binary form. Therefore we need to add this error also to the total error. What we mean, if even if you are taking a number like 0.1 or 0.5 to the computer, it is changed into binary form, when and then it is going to be cut at the 23 bits. Therefore the computer is automatically introducing an error which is the machine epsilon. So that is the accuracy of the machine is being included. Therefore this error is also, when we are in the previous slide we have written the total error plus other errors we have written. Now the total error will now include this error which the computer is automatically making while converting a number into its binary form. Now then I also said that we should take some other errors which could be the, what are the other sources of errors that we can arise. Some sources of errors are some very simple calculations. Care must be taken even in simple operations which may also be source of errors. What are the simple operations? One is subtraction of 2 nearly equal numbers. If you are subtracting 2 nearly equal numbers in a computer, then we are going to have it is a big source of error, because we are going to have loss of significant digits. Let me give it an example and then say what I mean by this. Let us say this x and y are the exact numbers, and x star is an approximation to x, y star is an approximation to this, and I want to subtract these 2 numbers and get what will be the value. So what I would be getting in the computer is a z star, which is the subtracting x star minus y star. Let us now suppose take 2 numbers, x star I will take to 6 decimal places, 264593 into 10 power 1, that is 2.64593, and y star I will take 2.64162, that is in this particular form. Both are corrected to significant digits, because we are now talking in the normal form, because that is what the computer uses. So we are using the normal form of a decimal number. Therefore we are putting this into exponent 10 to the power 1 into 10 to the power 1, and this is corrected to 6 significant digits. Now I want to subtract these 2 numbers. Now if I subtract these 2 numbers, z star will be x star minus y star is 3.000431 in 10 to the power 1. Now when it converts to the normal form, this goes as 0.031 into 10 to the power minus 2. So this is in the usual form that we are writing, but when once it is written in the normal form, it is going to be read as 0.431 into 10 to the power minus 2. Therefore this is correct only to 3 significant digits. Therefore we have lost 3 digits in this subtraction of the small numbers. Now you can see, I mean, how we are able to say that this is not accurate. Let us look at its relative errors. Now let us look at what is the relative error in x and relative error in x minus y, that is this number that we have got. That will give you an idea how accurate that this computation has been made. Now if I take in the value of x, the now if you just go back to this slide, this x star is given this significant digits, and this is 2.64593. Therefore I can immediately write down what will the error in this. Error will be, when we are talking of this, we are talking about the magnitude absolute value, it could be on the other side. So 0.5 into 10 to the power of minus 5, that comes from here. So and the true value is 264,593. So if I subtract divide these two, then what I would get is 1.89 in 10 to the power of minus 6. This is the relative error in x when we have started the problem. Now let us find out what is the relative error in x minus y. Relative error in x minus y will be the error in x, we are talking about the absolute value, therefore magnitude of the error in this plus magnitude of the error in this and divided by the actual value. Now if I now substitute this we get as 2.32 10 to the power of minus 3. Now which is very large compared to the relative error in x. The relative error in x was 10 to the power of minus 6, and whereas here relative error is 10 to the power of minus 3. So it is now reflecting how inaccurate is this value that we obtained x minus y. Now normally this is very trivial and very strict subtraction which we are doing, and this we are going to do tremendous amount of computations in our this one. Now if this value of z star is used in further computations, error would definitely increase. Now therefore this is a very simple case when loss of significant digits can occur. The second example that comes is the division by a small number. When we divide by a very small number, then also we are going to have tremendous amount of error in the problem. Let us take a very simple way of illustrating it by taking an example. Let us suppose we want to evaluate this function f(x) is equal to 1 upon 1 minus x square. Suppose we want to find the value of f at 0.9. So I would first find what is its exact value. The exact value of this will be simply just 1 upon 1 minus x square. So I compute this and write this as my exact value of the 1 upon 1 minus x square. Now let us commit an error in x. That means let us take x is equal to x star as 0.9005, and the error is 0.5 into 10 to the power minus 5. If I now substitute this and evaluate it, then I can evaluate it. F of x star is 1 upon 1 minus x square, and I evaluate it 526341 10 to the power of 1. Now the error in the 6th place has now produced an error in the 5th place. This is 5263 and 1 and here 4. So error in the 6th place in x. Now here we have committed error in only in 6th place in x, whereas here this value, function value of a simple function 1 upon 1 minus x square, it has produced an error in the 5th place of this. Now you can see how these errors are playing about. A accurate plus up to 6 places have now reduced accuracy to 5 decimal places. Now these are being used elsewhere. So when you go on using them like this, the accuracy that we have started with, it can go on decreasing further. Therefore when the huge computation is completed, we really do not know whether what our solution obtained is correct or not, how many decimals is correct. The computer may be outputting 10 decimal places. Is it correct all the 10 decimal places? Is it correct only to 2-3 places, because we have lost so many significant digits? So that is what the point that we are trying to make here. Now what is now the cumulative effect of all these errors in a large computation? What we are talking of? The round off error, the truncation error, other sources of error, the machine epsilon. There are so many errors that would be there in the computer when we have gone to the computer. Now what is the cumulative effect of all these errors in a large computation? We will now define that if the growth of errors is under control, that is bounded, then the method gives stable results. Otherwise numerical instability occurs. What do you mean by numerical instability in a computer? It gives you overflow. So it just say it is overflow, and it goes beyond the limit of the computer, and then say overflow has occurred and the computation will stop, and then the output will be known that it is exploded. Now the numerical instability, what we talked about is about numbers. Now the next thing we would like to talk about in numerical instability is that you have a problem, we want to use a numerical method. The numerical instability can occur not because of the numbers which you are using, but because of the problem itself was not constructed properly. Properly means in our sense it may be proper, but when it has gone to the computer it has become improper, or we might be using a wrong numerical method, because a problem may have many methods that we can use it, of which few methods only would fit in for your particular problem. Let us take a very simple example. You will be wondering how, I mean, such things can happen when we go to the computer. The two instabilities that we will define as inherent instability and induced instability. Inherent instability means instability is inherent in the problem itself, whereas induced instability is instability induced by the user. That means he is using a wrong method for solving that particular problem. Let us illustrate it to an example. Now let me take this example, a very famous example called example of Wilkinson. It is finding the zeros of this polynomial. He has just taken the product of x minus 1, x minus 2, x minus 20. If I expand it out, this will give you x to the power of 20 minus 210, that is sum of 1 plus 2 plus 3 plus 20, that is 219, x to the power of 19, and the constant is 1 into 2 into 20, that is factorial 20. So this is the polynomial that we will have. We know its exact roots are 1, 2, 3 and 20 if I find the roots of this particular polynomial. What we do now here is we just change this only one coefficient of x to the power of 19 from minus 210 to minus 210 plus 2 to the power of minus 23, where 2 to the power of minus 20 is of the order of machine epsilon. Therefore, we are not committing an extra special error, we are just adding a number to it which is the accuracy of the machine, that is the 2 to the power of minus 23 is as the error in the particular problem. Now let us solve this problem by we shall discuss later on number of methods. So let us, some of these methods have been used to solve this particular problem. The very interesting thing happens is if you solve by any method as given now we discussed, all the smallest roots, that is 1, 2, 3, 4, 5, all the smallest roots are obtained with good accuracy, very good accuracy. Now accuracy starts decreasing as larger roots are obtained, as we go up 7, 8, 9, 10 like that. For roots greater than or equal to 12, the roots become complex pairs. That means it no longer becomes real, it is complex pairs. The largest change occurs in the roots 16 and 17, which are obtained as the complex pair, the real part is 16.733 so on, and the imaginary part is 2.81 so on. So that this is a complex pair and this represents the roots both of them 16 and 17, and if you take the magnitude of this is approximately 17. So both these roots 16 and 17 comes out as complex pair whose magnitude is approximately 17. Now if you are solving, if you change the method and as given, it is not going to give us, the solution is not going to come in the way that the problem has been tackled. Therefore this is an example of inherent instability, that means the problem as taken was not proper. We should modify the construction, the way in which the solution should be adopted for finding the roots of the polynomial should be changed so that the problem can be solved. Therefore this is an example in which the problem itself is having a difficulty in this. The second example we shall give is a induced instability. Now when I said induced instability, we would like to show that given a method, given a problem, it is not that we just pick up a method and try to solve that particular problem. We have to see whether this method is suitable for solving that particular problem. Let us see very interesting, very simple thing. We want to evaluate this integral 0 to 1 x to the power of n x plus 6 for n is equal to 1, 2, 3 up to 10. So that is I10 is 0 to 1 integral x to the power of 10 divided by x plus 6 d of x, and I want to use a recurrence relation for this. So I want to build a recurrence relation for this so that I can evaluate this particular integral. So I can now write down what is I n minus 1, that is 0 to 1 x to the power of n minus 1 x plus 6 dx. What I would do is I will add I n plus 6 times I n minus 1 into n. If I do that, I have been doing this so that I can integrate this easily. So this the integrand becomes, numerator becomes x to the power of n, 6 times x to the power of n minus 1 by x plus 6 dx. Now I can take out x to the power of n minus 1 common here, so that x plus 6 cancels here. So, what is left out is x to the power of n minus 1 of dx, therefore, which I can integrate and write x to the power of n by n 0 to 1, the value of this is equal to 1. You can see why we have multiplied by 6. I want to remove the denominator from this, so that I can exactly integrate this as that. So, I take this get this and get the value, therefore, I have the reconciliation n times I n plus 6 times I n minus 1 is equal to 1. Now, I want to use this reconciliation starting with I 0 and so on, get the value of I 10. So, what I would first do, now I want to use this relation, this you can just let us just put it over here. So, this I can, from this I can take this n to this side 1 upon n and take this 6 to I n minus 1 to the right hand side. So, I simply have I n is equal to 1 upon n minus 6 n minus 1 as a recurrence relation with I 0. I 0 can be integrated exactly. So, I can write down I 0 is 0 to 1 dx upon x plus 6. I integrate it as logarithm of 7 by 6 as, let us retain 5 decimal places 1.45. So, I want to get the values of the integral for n is equal to now 1, 2, 3 up to 10 using this reconciliation with the starting value. Now, I set I is n is equal to 1. So, I get I 1 is 1 minus 6 I 0. So, 1 minus 6 I 0 I substitute it here and get 0.7510. I 2 will be equal to 1 by 2 minus 6 times I 1, I 1 has been obtained. So, I can get I 2 is 0.4940, I get the values of I 3 as this. Then I proceed further and I land up finally the value I 8 is equal to minus 1 0.00972 and I 9 comes out 6.70943, I 10 comes out to minus 40.15658. Now, but let us just go back to the integral once more. If you look at the integral that is given to us, this is the integral given to us. As n tends to infinity, we are integrating from 0 to 1. Therefore, x to the power of n is going to be 0 as n tends to infinity. In other words, as n tends to infinity, the value of the integral I n has to tend to 0. So, we know from the given integral that I n should tend to 0 as n tends to infinity. Now, what has happened here? The solutions, as we go even up to I 10 only, just in I 10 only, it has started oscillating, negative, positive, negative, positive. So, they are oscillating and exploding. So, it has already reached 40. In the next step, it is going to go beyond 150, then few hundreds. So, when we said that the errors are coming and it is going to explode, this is what we mean by the explosion. Explosion is, if you now compute really up to I 20, I 25, you will find that number goes out of the bound and it will give you a the overflow on the computer. Therefore, instability has occurred in such a trivial and very, very simple example. Now, we shall say that this is a wrong choice of solving the recurrence relation that we have taken. So, what we would now do, the recurrence relation that we had here, this recurrence relation, we will write it in the reverse form and write it as I n minus 1 in terms of I n. So, I will write down I n minus 1 is 1 upon 6, 1 upon n minus, that means I would like to work backwards. Why I should work backwards here? I know that I n tends to 0 as n tends to infinity, it is a decreasing value. So, what I would do it, I will boldly commit an error here and say, since I n tends to 0, n tends to infinity, let me approximate I 10 as 0. I mean, it could be something else, you can take it because very small, but let us take 0 and see how it is going to affect our solution. So, I can now work backwards and then we will get here I 9 will be 1 by 6, 1 by 10 minus 1 by 10, I 10. So, this was taken as 0, this is simply 1 upon 60, that is 0.1666. Then I work backwards I 8, 1 by 6, 1 by 9 minus I 9, this substitute here, I get 0.1574. And now I work backwards, I get I 1 is 0.07510, I 0 is 0.1545, which is the exact value. See here, we are, when worked backwards, I have got the exact value of I 0 working backwards. Therefore, this would tell me that if you are solving even a simple problem, one should not take it as an obvious problem, and when we are putting it in a computer and going to solve this problem, it is the correct choice or correct way of writing the problem that will give you the solution. Therefore, wrong choice of a method can also induce instability. In fact, many of you would be doing in your projects later on, wherein you have to use lot of numerical methods. These are some of the serious difficulties that you would encounter there, that you produce a solution and say that this does not match with what I was expecting. I am expecting a different graph for the solution, I am getting it. Therefore, you will have to look into the various aspects of the errors that can arise in a problem, including a proper method that is being used or not. Now we would like to consider the first topic that we would like to study, that is the solution of nonlinear algebraic equations. Now when we talk of the solution of the nonlinear algebraic equations, we would like to first consider an equation in one variable. Let us take the equation as f(x) is equal to 0. Later on we shall take system of nonlinear algebraic equations, but let us first take an equation in one variable only, f(x) is equal to 0. Now here this f(x) may be a polynomial, we may be taking a polynomial, that is a0 x to the power of n, a1 x to the power of n minus 1, a n minus 1 x plus a n. So it could be a polynomial for which we are finding the roots. For example, earlier we talked of finding the roots of a polynomial. So we are now talking of a polynomial, or we may be talking of a transcendental function. f(x) could be a transcendental function, that means it will be a function of polynomials, combination of polynomials, exponential functions, trigonometric functions, logarithmic functions. A combination of all these functions, we shall call it as a transcendental function. For example, f(x) is equal to x minus tan x, it is a transcendental function. It is a combination of a polynomial and a trigonometric function. So any combination of this shall be called as a transcendental function, and otherwise we will be considering a polynomial. Now we define some of the concepts for the finding the roots of the polynomial. So we would like to first define a root or 0, which you know already, but let us just revise what we mean by that. We shall take x is equal to xi an exact root or a 0 if f(x) is equal to f of xi is equal to 0. So we will use both the words 0 or root for the equation. Now this root will be a simple root. Mathematically f of xi is 0, but f prime of xi is not equal to 0. Its first derivative at that value is not equal to 0. Therefore, x is equal to xi is a simple root. That means if you are factorizing the given polynomial or a given function, you can take out the factor x minus xi as a factor, as a simple factor. For example, x is equal to 1 and 2 are the simple roots of x square minus 3x plus 2, because this I can write it as x minus 1 into x minus 2. Therefore, I will say that x is equal to 1 and x is equal to 2 are the two simple roots of this particular equation. Now I would like to talk of the root of multiplicity m. So it is a multiple root of multiplicity m. So we define that f of xi is 0, f prime of xi is 0, m minus 1th derivative of f at xi is also 0, but mth derivative at xi is not equal to 0. Therefore, it will be a root of multiplicity m. Therefore, the up to derivatives up to m minus 1 will be 0, mth derivative will be equal to 0. Then of course, in some cases we may be able to write f(x) is equal to x minus xi to the power of m into gx is equal to 0, g xi is not equal to 0. That is, we are just as we mentioned earlier, because of this property it is a root of multiplicity m. Therefore, I will be able to take out, factorize this as x minus xi to the power of m into gx, but g xi is not equal to 0. However, we can also look at this same problem in a slightly different way, and that is, we know that if a function f(x) has a root xi of multiplicity m, then its derivative f dash x has the same root xi with multiplicity m minus 1. So the derivative has got multiplicity m. Similarly, if I go further, the second derivative of w dash x will have multiplicity m minus 2. Now what I do is, I will take a ratio of the f(x) and f dash x and then construct a new function. So I can now define hx as the ratio of f(x) by f dash x, then hx as a simple root xi. Therefore, here we are now already suggesting a method that if I have a method for finding a simple root, I can use the same method for obtaining the multiple root also, but if I use a new function fx hx is equal to fx upon f dash x. That means if I know that a particular function has a multiple root and I do not know its multiplicity, then I would take the ratio of fx by f dash x. Fx by f dash x has to have only a simple root. Therefore, I can use the method that we are now trying to use for finding a simple root for also the problem where it has a multiple root in which multiplicity is not known for us. Now similarly, for example, x is equal to 2 is a multiple root of multiplicity 3 for this particular equation. Now before we talk of what is the method that we would like to construct, let us now see what we mean by what the root of a function f x. Let us just look at the graphic representation what we mean, because any method that we are going to construct here we will able to pictorially give what we mean by this numerical method, what is the numerical method doing and how it is getting a root of this particular problem. So if I just plot the graph of y is equal to f x, x take a, and along the y axis we take f x, the graph cuts the x axis at a point and that is my exact root, that is f x is equal to 0. So y is equal to f x is equal to 0, y is equal to 0. So the graph is cutting the x axis at a point and that is the root. So what we are trying to find out, the simple root is trying to determine what is my xi. Now in the methods for solution for finding the roots of simple root or multiple roots, there are two types of methods. One is called the direct method, the other is the iterative methods. The direct methods produce solution in finite number of steps. So we are now trying to distinguish the direct method and the iterative method. The direct method produce solution in finite number of steps. Let us take a very simple example for that. Now for example, I want the roots of this simple quadratic a naught x square plus a1x plus a2 is equal to 0. So I can write down that x is equal to our standard formula. I can write down this formula and say these are the two roots. I would say that this is a direct method. I am getting both the roots x1 and x2 by just finding this particular value, finding its root and then getting this value. Now in a direct method the operational count is possible. What we mean by operational count is what is the total number of multiplications, divisions, additions, subtractions that are there in a problem. Thereby you would be able to really say what will be the computed time that will be taken by this particular method, because we know the speed of the machine. Since we know the speed of the machine, we can immediately count the major operations, the addition and subtraction, the major operations as the multiplication and division and the minor operation is the addition and subtraction. So therefore we can be able to compute the whole time that is there and then say this particular will take this much of time. So therefore operational count is possible. Sorry. For example, here I can count what are the operations involved. I have a 2 multiplications here, 4 into a naught a2, 2 multiplications are there. I can take a1 square as a multiplication, a1 into a1. So I can take this as a multiplication. So I can say there are 3 multiplications. There is one division here, and addition subtractions, there is one addition here and one subtraction over here, addition or subtraction. So I got addition subtraction to 1 square root. So I now know this particular formula has this operational count and I will be able to say what will be the exact amount of computed time that will be taken, whether it will take a few microseconds or few seconds or this, I will be able to give it. Therefore a direct method always, it is always possible for us to give an operational count, but there are no powerful direct methods available at all for us to solve a difficult problem of a single nonlinear, even a single nonlinear equations, leave alone a system of nonlinear equations. Now let us now define what is an iterative method. In the iterative methods we use the idea of successive approximations to a root, starting with one or more initial approximation to a root. So what we mean by this is that we make an initial guess of the root. How we get an initial guess we shall see, but we shall make a initial guess to the root and then try to refine it using a numerical method, refine it further and further so that we will approach the exact root of this. So we shall call this as an iterative method. That means taking x naught as an initial approximation, we obtain a sequence of approximations x1 x2 to the true value of the root. Now let us go back and try to write down this example that we have now written, a naught x square plus a1 x plus a2 is equal to 0. Let us try to write down iterative method for obtaining the solution of this problem. Now I will just put this below this here, and because so that you can see. Now there are three formulas I had given. If I take the first formula, what I have done here is I have taken these two terms to the right hand side, divided by one of this x there, and then retained this as x on the left hand side. So I will have here minus a2 minus a1 xk divided by a naught xk. So I would take this as an iteration formula. Whether it is going to converge or diverge, we are going to see later on. So but this is an iteration formula. Starting with an initial approximation x0, I can go and find x1, substitute it here x1. So iteratively I can get the sequence of approximations x0, x1, x2, x3 and so on. And then alternatively I can write another formula here, in which I have retained first and third terms I have taken to the right hand side. I have retained the middle term on the left hand side, so that I can divide by a1 and write xk plus 1 is minus a naught xk square plus a2 divided by a1. So this is also another iterative formula that we can construct for this. And thirdly, I will take this if I will take this particular term to the right hand side, retain these two terms on the left hand side, and then I will take the common factor x here and then divide by this one. So I will have xk plus 1 is minus a2 upon a1 plus a naught xk. Now where all these formulas are of the form xk plus 1 is some function of g of xk. Therefore it is possible for us to have a large number of iterative methods. Given a problem, it is possible for us to construct any number of methods. Now it is an infinite sequence of approximations. I think we will stop at this lecture today. In summary, what we have done today is to define what is a numerical method. We have also defined what is the error of approximation, what are the sources of errors, how serious or how important is the cumulative effect of all these errors. Then we have also defined what is a nonlinear equation, single nonlinear equation, and defined what is a direct and an iterative method.